I just posted, thank you everyone for joining the workshop. It is my first time doing that. And as you all know, MGWR is a wide and vast topic, which is actually a graduate course that Stuart does in the fall semester. So it's impossible to do that in 1 hour. So my entire idea to do this workshop is to actually communicate some concepts. And sometimes I think people have this doubt of when exactly would we use MGWR, or what is it exactly that we're doing with the software. So those are hopefully some answers that I would like to give through this presentation. And then we will also run through an example data set with the software, so you guys get a hands-on experience with it. And then I'm happy to help after this workshop if people want to try their own data sets and are excited to do other things with it. I just posted a link on the chat here, which is basically a gist to the workshop, and I'm now going to share my screen so people can see it. Okay, I hope you all can see this. So the link that I posted on the chat should reach this page. And please feel free to unmute yourself at any point and jump in with any questions. I may not be able to follow the chats very well, but I'm very happy to make this interactive because I just hope for this to be a more of an informal kind of a workshop. Great. So this is basic. I built the entire workshop in Google Collaboratory, which is a kind of a notebook which is on the server. And I was initially going to do it in Python, but I thought that was a lot to cover in 1 hour. So we will be running it on the GUI software. It would be great if you can download the software for your system on this link. It basically will take you to this link, which is our Spark website, which has all these software, and there is also the manual for NGWR. So if you have Windows, I would encourage you to do according to your system, just download it for now, and there will be an exe file that so just run the exe file in the background so that it is ready for when we get to the part of running the software. Great. So I will go. If you guys want to follow the gist in a different format that I'm going to be showing, it basically you should just click on the button up that says open in Google Colab. Oh my God, it's not even a second. Okay, yeah, this is basically anyway, I'm just going to jump here. Is anyone having problems with the gist, or can everyone see the material that we are looking at the shared screen now? All good. Okay, I'm gonna assume everything is fine until there is a problem. So just feel free to talk in or interject me. Cool. So I'm going to start with a basic introduction of why or when we would like to use MGWR and what kind of research questions we would like to answer. So basically, the data that we observe in the world around us are basically spatial patterns. And we often want to ask questions like, why do those patterns exist the way they are? So there are underlying spatial processes that are affecting those patterns. And to understand why those patterns manifest the way they do, we would often want to model those processes and see what is it that is causing this data to be in the way that it is. So this is a very schematic diagram of what I mean. Basically, there are spatial processes that are affecting the spatial data that we see and observe in the world. There is no way to basically measure those spatial processes, so we model associations, which are spatial associations. And that is what leads us to an inference of the spatial processes that are affecting the data that we observe. So I know this all sounds very abstract, so I'm going to go into a very simple example. Here is an image of the New York Manhattan skyline. So as we see here, again, this is very simplistic. I just went on with a factoid. So this may be wrong, but I just want to get the concept across about spatial patterns versus spatial process. So here we can easily observe that there are a lot of high-rise buildings and a high density of high-rise buildings in Midtown to Uptown and Downtown. And there is this big lull in the middle in Manhattan where we do not see many high-rise buildings. So this is a spatial pattern that we observe, and it's not random. Clearly, there is something going on here which is basically affecting a lack of construction of high-rise buildings. And we would often want to ask the question, what is leading to this pattern? right? And as it turns out, there would be many processes that would be affecting this, like, air rights or something to do with economy, or there are like various reasons that are possible. So we would often want to model that. One of those reasons, as it turns out, is the bedrock as it exists in Manhattan Island. So basically, how that exists is that there is a lull in this area where you would require a much deeper foundation to get to a stable bedrock to make high-rise buildings, and that is what makes the construction of these high-rise buildings not viable. So the process here, which is affecting the pattern that we observe, is the geology of the island, and that is often something that we would not guess in the first look at the spatial pattern of the data, and we would want to model that through certain techniques. Now, a more realistic example would be something like human migration. That's a like social phenomena, and that is something that we would want to actually study, as researchers. So what there are many reasons that could be causing mass human migration between two cities, for example, and they could be waiting at different spatial scales. So it could be a conflict at a local scale, which would be urging people to move from one city to the other, or it could be something as global as climate change that could be affecting water resources or land resources that people depend on, and they cannot anymore, so they have to move. So there are many of these processes, like economic opportunity or many things that could be affecting the pattern of human migration that we observe. So in the world of modeling, and like how we would model some phenomena like this would be in terms of regression models. So regression models are like a huge umbrella of models that basically want to establish these associations between patterns and processes, not necessarily spatial. And spatial regression is a form of is basically an array of models within the regression models, right? So in a regression model, what would happen is that these would become our independent variables, like conflict or economic opportunity, and human migration would be a dependent variable, because that is dependent on all these different processes that we want to measure. Um, so regression models are basically, so I'm just going to dive into the problem that we're going to be working on in the example data set, which is on house price modeling. So regression models are often used in many fields, and hedonic house price modeling is just one example of it. So this is an equation typically of how regression models function. So this is the dependent variable, which is y. The x's are the independent variables, and this is an array, so you can have more than one. And beta is basically the measure of the process, or the spatial or the association between independent and dependent variable. So in terms of hedonic house price modeling, so just a primer of what is hedonic house price modeling. So because in house prices, you cannot basically, there is no way to measure what is the cost of a bedroom, or what is the cost of a bathroom, or what is the cost of having a garage or not. You just know the price of an entire housing unit, and often we want to understand what is the marginal cost of these different structural or neighborhood attributes that form this housing unit. So hedonic price modeling is a larger umbrella of models which are used to segregate these marginal costs where it is not apparent or it's not obvious to do so. So for example, a hedonic model would basically inform us of the cost that would, how the price or the housing price would increase if you increase the living area by 1 square foot. Or like, what is, if all the other things of a house are constant, and if you add a swimming pool, what is the marginal cost, or what is the marginal value that you would get for that? That is a very simple example of how regression models would help get to those marginal costs. And that is one of the things that we are going to do now. Not to say that's the only reason we would use regression models, but it's one of the good examples. I'm using that in the workshop today. So here's X. For example, if X is square footage of living area and Y is house prices, and suppose we have a beta, we model it and the beta comes out to be +5. How we would interpret that would be 1 unit increase in square footage of living area. So 1 increase in a housing living area of 1 square foot would lead to an increase of house price by $5, or whatever the unit your Y is in, mostly dollars if it's house prices, right? So if it is positive, that means that an increase in X would cause an increase in Y. If the beta assumes a negative value, you can say that an increase in X actually decreases Y. So that is how you would interpret these associations, and that is exactly what we are after when we are doing regression models. Now, for example, this is still the case, and we have about 100 house unit prices for an entire across a city, and we want to measure how living area affects house prices in that city. The obvious problem here is that you get a single data for the entire 100 house prices. Right, so that would be equivalent to saying that no matter where your house is, if you increase your house price by 1 square foot, you would get $5, no matter where your house is in the city. Now that's obviously a very big assumption, and it's convoluted because that's almost never the case in many of the social phenomena that we see, and not only house price like house prices. So I mean, just to visualize what I mean by this difference and what I'm trying to cite here is, suppose we have, so this is the map of New York City, and suppose we ran a hedonic price model, and we found that the global regression model gave us this estimate that 1 square foot increase in living area would increase your house price by $1,000. Now, whether your house is in downtown Manhattan or in Staten Island, you have this one single estimate. Now that is kind of insane, right? If you know the entire context of the city, you would know that one size of a house in downtown Manhattan is so much more valuable than in Staten Island. So how you would get around this problem and beat this assumption is by using local regression techniques or spatial regression techniques, and GWR is an example of it. So a local regression model would basically give you a map of something like this. This is not model. This is only for the purpose of representation, but it is of value to see what this means. So here you see the red, red come up in downtown Manhattan, and there's a blue in Staten Island. So which would basically, you would get an estimate for different, whatever scale you have your data on, you would get an estimate for each of that unit. And this basically picture would then tell you that 1 square footage of increase in living area would lead to an increase in $1,600 in downtown Manhattan, whereas only $450 in Staten Island. Now, this is a clearer picture of what how the processes are affecting spatial patterns, and this gives us so much more information than what we were seeing here, a single average coefficient. And I mean, this actually means nothing if you come to think of it, whereas this can actually tell you a lot more about the processes and the patterns that you are seeing and how those vary across space. So this is basically why you would want to use MGWR, and this is why you would want to use actually any local spatial regression technique over a global regression technique. Now I'm going to quickly run over how GWR does it, and it's basically, I'm not going to get into a lot of technical details, but if you have any questions, I'm really happy to answer. It's just that the time is so limited that I do not want to get into that in detail. So basically, what GWR does is that it calibrates this global model at every point, right? So if this is your study area and you have each of these data points, a model is calibrated at each and every point. So if you're calibrating a model at each and every point, you get a parameter estimate, the beta estimate for each point, for each covariate that you're using, right? But it's of value to us that how are we getting enough data to calibrate a model? Because here I have a single data point, and that point is never enough to calibrate any model. And we hardly ever have that kind of data where you have at every unique location, you have 100 unique data points. That's almost never the case in any of the data that we see. So how GWR gets around this problem is that it borrows data from around a single point. So that is in line with Tobler's law, that similar things are, they tend to be closer than distant things. And so for the red, for example, the radius, it would basically draw a radius of how many points to use, would use those data points to calibrate a model at this one red point. Then the red point would probably shift here, and then it would draw another circle, and it would take those data points and calibrate a model again. And that it would do for each and every data point across the study region. Now, how it chooses how many points or what is the distance of this radius is through through optimization algorithms such as AICP or cross-validation. And those optimization criterion often lead to this parameter called a bandwidth. So how many points, or what is distance being used for every calibration of the model is called the bandwidth. And that is often interpreted as the scale at which the process is affecting the pattern in the most significant way, right? So, I mean, as you see, if there are like so many points, and if this is the bandwidth, you can figure out that okay, this is where the processes are kind of similar. And then if you like move out of the circle, the processes kind of change. So then it's kind of a regional scale from what I can figure here, right? Now, if you go back to this example, you can see if this is where my cursor is, if that is where we are calibrating a model, and if I take only 5 nearest neighbors, this is going to be a small scale. And if we say that the processes are only similar across the scale, that would be a very local scale for a process to have. But if we say that the nearest neighbors used in this model are 20, that would basically mean that okay, this is like a regional scale, that Brooklyn, parts of Manhattan, and Staten Island have kind of the same scale, like so they all come into the same process. So basically, it's kind of a regional scale. So that is how the bandwidth parameter that comes out of MGWR, that is how it is calibrated, and that is how it is interpreted. Now, the difference between GWR and MGWR is that GWR used, like in the previous version, we used to assume that all the processes, all the covariates. So you can use multiple X's, like I told you in the previous model specification. So for all those processes, we would assume the bandwidth to be the same. But that's not always true. Like you can have all these different kind of processes at play. Like we also saw in the human migration example, processes can be local or global, and it's of value to like understand each of these processes for the scale that they are operational at. And that is where MGWR comes into place, where it releases this assumption that all covariates operate at the same scale. So, in an MGWR model, if you were to model hedonic house prices with square footage of living area and age of structure and distance to the nearest waterfront, 3 variables, you would get 3 different scales at which each of these processes affect house prices. So you would probably get like, a regional scale for age. I mean, who knows, whatever you would get. But you would say that most of the city responds to age as a stimulus in the same way than square footage of living area, which is very local, that it changes with every neighborhood. So that is basically the difference, and that is why MGWR is more of value, because then you can also segregate each and every scale of your process that is under examination. So I guess this is the conceptual introduction, and I know that was a lot to go through in I think like 18 minutes. I rushed through a lot of material, but if there is anything that you have, any questions that you have, or anything that was not clear, I would be happy to answer any questions, and then we can deep dive into the software part of things, where things actually you can see the results and summary and stuff. So I'm going to wait for a minute or so if there are any questions, and if not, we can move right on. Okay. Cool. Looks like everyone is kind of on board with why we would use MGWR and for what kind of research questions. So that's great. Cool. So I hope everyone has downloaded the software, and if there was any problem in running it, I would like to know it now. Otherwise, we can and here is where we will start actually running things on the software. So I will be doing it like here on the shared screen. So if people want to just see and follow along, that's fine. But if you also want to do it on your computer, that would be great. So if you have any errors that come in, I would love to know if so here is a link to an example data set. If you just click it, it should directly download as a CSV file on your system, and it will probably be in the downloads folder or wherever you set it up to be. So this data set, if we just open it quickly, it is basically so this is basically a hedonic house price, like it's a house price data set for the King County region, where Seattle and Bellevue and Redmond and all these cities are in Washington state. And it is at the census tract level. So these are averages across of housing unit prices and their structural attributes across each census tract in the King County. So we have different variables here, like average price would be our dependent variable, because that's the average house price across a census tract. And then we have different variables that we would model, that is average, whether there's a basement or not, or whether like what is the average basement in a housing unit in a census tract. and what is the average square footage of living area, what is the average distance to waterfront, because there are many lakes in the King County, so this is an important variable that comes into play. So the other part that I'm not getting to in regression modeling, which is very, very important, is variable selection. And that is often informed by literature, or you already know something about a phenomenon. Like house prices is a very, very, very common example that people have dealt with for decades. So there is a lot of literature which would tell you that, okay, age of a housing unit, bedrooms, bathrooms, living area, all these are like obvious things to definitely add in your model. But then there are some other things, like for example, in the King County, I found that there were so many lakes. So, distance to waterfront becomes a very important contextual feature that you do want to add into your model. So there's a lot of science and art both in selection of variables for regression, and that's often like sometimes people get confused, but it's, a lot of trial and error that you have to do with these models. And then there is average unemployment rate. So you often want to also use, census variables such as unemployment, or in this particular case, I also use average technology related jobs, because there are so many companies such as Google, Facebook, Microsoft, Amazon who are situated in that area, that would play a major how prices are defined, because if there are a lot of people working in these high paying tech industry, they would be willing to pay higher for proximity to work and stuff like that. So those are some of the variables that we'll be using, and this was just to show that this is the data set. I'm going to save it. So everyone should have gotten this, and now I'm going to run the NGWR software, and you should see that on the screen in a minute. So if you run the MGWR software, you will see a window, something like this. I'm just going to reduce in size. Okay. I don't know why I can't reduce it now. Okay, well, this will work. This is a very intuitive and a simple GUI version of it. So this should be fairly straightforward. But for data files, this is where we would we would load our files. So the three dots, basically, if you click there, that will take you to your computer's window. And in downloads is where my file is, because that is where it got downloaded. So I would click on example dataset and say open. This is where it reads the CSV file, and it reads all the variables, all the columns that are there in the CSV file. Now this is optional, but this ID is basically just any unique number identifier, column of your data set. And in our case, this is the int column. This is basically for latitude, longitude, or if you have projected any coordinate system, right? So in this particular data set, we have spherical because we have it in longitude, latitude. So I would change that to spherical, and I would put longitude here and latitude here. So you basically select the variable and you'll click the arrow. And if I want to remove it, I can just do the other arrow and it gets removed. So it's like fairly intuitive. So you fill in these fields here. We want to run the MGWR model. Now, what are these kernels? So they have an option of adaptive and fixed. Now, basically what kernels are basically, it depends on the kind of points that are there, or what is your data, I would say how your points are arranged in your study area, right? So if you have a fairly, so how adaptive would work would be like it will take a fixed number of data points, no matter how far they are, right? So if in this case, it's going to take 5 data points. So it will have a very narrow kernel of weighting here because it has already gotten 5 in a very small distance. But in this case, because the points are dispersed, it will reach far out to see how it can gather those 5 points, and the kernel will be more spread out. This is mostly the case with spatial data that we use because our data is not like grids. If you have a data set which is mostly like grids and you want to use it on that, I would suggest that you use the fixed, where the kernel width remains the same no matter how many points come into it, and that is then defined by the distance from this is where the regression is happening and the far out distance that it's going to use for the kernel. So in our case, we use adaptive. That is mostly how you would use it if you're using census tracts or zip codes or even plain simple point data. But if you're using grid data or something like that, which is more symmetrical, you would go in for fixed. So I choose adaptive, by square is fine. This is just the kernel function. So this is basically, we have only one option with the adaptive. Now in this, we would, for the y variable, it is our dependent variable and that is average price. I would load in that. Now I'm going to take in all these variables. I have already come up to the conclusion that I'm going to use these variables, so it becomes easy. But it took a while for me to understand which variables to use and which not to use. So we're going to use these. They're all important and they will all come to be significant because I've already done those trials once before. But you can use that. You can try and see if how your model responds and what variables you would want to add. But that takes a while. So of course, it was too less of a time to go through that. So I'll load all these variables, which are my independent variables in here. This is where my dependent variables are. This is where my independent variables are. The intercept, which is the constant, which is always there, and you should keep it that way. Now, this is the optimization criteria, which I was telling you about how the bandwidth is selected and how many points to use is selected through these optimization criteria. Now, I know people in statistics, and I mean, they have their reasons to choose one versus the other. AICC is arguably the most accurate, I would say, or the most convenient to use in many ways. So, this is what we resort to. But if you have a particular reason that you would want to use some other criterion, we do have an option for that too. Now in the advanced section, the standardization of variables is supposed to be on always. There are other things, which is for tests of spatial variability, and I'll come to this in a second. But so for standardization, it should always be on because for MGWR, you need the variables to be standardized. And why that is because we want to be able to compare the bandwidths that come out of the model. Because if our scales are not similar in terms of units, if they are not similar, then the bandwidths that come out will also not be comparable amongst them. So that is the reason why we always want this on. Okay, I'm just gonna leave it at that. And great. And then here in the summary file, you can just save where it should basically save it. And I'm just gonna say download. That's fine. And this would be, and I'm gonna rename my file to this. Sorry, and save. That's it. And then I would press the run button. And the moment you do that, it basically starts the backfitting algorithm, which is on the back end, which is basically trying to understand how many points to choose for each calibration. So here you see all the bandwidths come up. And here we have 357 census tracts in the entire King County region. So that is good to know, because that would be our reference. 357 is the total number of points. So whatever comes out in terms of these bandwidths would be in relation to that. So if we get something like 43, that's pretty local because 43 out of 357, if it's choosing, that's pretty local. But if we get, so this one, for example, is already at 353, which means that it's almost taking all the points that are available to it, which means that it's basically just a global, at a global scale. Just as a precursor, this does take a little bit of a time to run. I mean, this model will run quickly because it's only about 350 points. But MGWR in general takes a little bit of a time to calibrate because it has all this backfitting at the back end. So you want to have some time at hand. So if you have about 2,000 or 3,000 points, it could take about 4 or 5 minutes to calibrate, and it's not linear. So if you have 10,000 points, it would probably take an hour or so. So this one will happen in a minute because it's only 350 points. So now it's computing the inference. It's already done with the bandwidths, and these are our final bandwidths. And we see they're like pretty varying. So some of them are in the 40s, and some of them are like 250, 200, 350. So it's a mixed scale. So this is interesting because these bandwidths tell us a lot, and we'll get to the inference and interpretation of these results. But this is the major reason why you would use NGWR and not GWR, because as you can imagine, instead of all these different bandwidths, you would have gotten just one bandwidth in GWR, which would have been an average across all covariates. Cool. So this is the document that we get the moment it is run. It's a summary document that basically tells you the results and shows you in comparison to a global regression model. So it starts with a global regression model. First, it tells you, okay, what kind of a model you used and how many covariates you used, what is the number of observations, so 357. sorry. And so how many variables did we use was 8 and so on. Now, you see the R square is an important thing. So in any regression, R square is basically the explained variation. So how much of your Y has been explained by your covariate. So, and it's usually multiplied by 100 to give a percentage. So this means that our global model, just global model, not even using MGWR, our Y was being explained by the X's at 82%, which is pretty good, which is really good. In most regression models and global models, you would, for social phenomena especially, you would get about 40-45% of explained variance in Y. And then, like, it increases with the spatial regression, as you'll see later. These are all the parameter estimates for the global model. Again, like you see, these estimates are a single for all 357 points for the entire King County. There is a single unit. There is a single coefficient. And so it says that, as if the average age of a housing unit in a census tract increases by 1 year, your price would actually go up by like 0.184. So these are all standardized. So it's like relative. So you see, average square feet has the highest coefficient, which means that 1 square footage of increase in living area would cause the house price to go up by 0.7. But the biggest limitation here, of course, is that it is saying that that would happen all across King County, while we know that that's almost never the case. So then we can come to the MGWR results. Here there are the bandwidths, and so the bandwidths are basically, so the interpretation of bandwidths is relative. And so when I say that as compared to age of a of you know of a housing unit in a census tract, the unemployment rate is more global, of course, because this is 353, this is 45, 43. And this index, I'll come to that variable later. Presence of basement is a regional variable, you can say, because it's 130. Now, there's no rule of thumb of what is regional versus what is local. That's dependent on your study area. That's dependent on in relation to other covariates. But this does reflect a very wide range of scales at which different processes are operating, and this comes in very handy when we have to interpret the results and the parameter estimates, because it is often of value to say not only how a process is affecting a pattern, but it's of value to say at what scale. So, for policy decisions, so for like any policy implications, you would want to know whether you're talking at a very local scale, or whether you mean that company needs to change something like that. So this is a very powerful thing that MGWR basically gives as a result. Now, our R square for this model for MGWR is 97%, which is, insanely high. It's also because, we are using a scale which is too, coarse for hedonic price modeling, because it's census tracts, and hedonic price modeling is often not done at a census tract level. But this is just for the purposes of a workshop, and we won't publish a paper with this kind of a data set. But 97 is a significant improvement even from the 82 that we saw for the global model. And that is always been the case in our experience, especially with MGWR, because there is a lot of spatial variation that is not being explained by the global model, that is being explained in our by MGWR. And that often leads to more explained variance, because almost always social phenomena that we want to unearth and uncover are almost never random. They always do have a spatial pattern to it. And when they do, and they are, we know about spatial heterogeneity and spatial dependence, MGWR comes into play and basically helps in explaining that too. So that is another major advantage of using this tool for that. Now, because the parameter estimates are all at individual scale, so for each of these covariates, we have 357 parameter estimates. Here we only give a summary. So we'll say like the mean is this and a minimum is this. So you can compare it to the global regression results just by mean and, by mean and max and min. But it is often of value to, you would always want to map these parameter estimates on those spatial units that you did the model on. So that is the other file. So this is the summary file that gives you just this much, the synopsis of what your model was, and it gives you the R squared. So if you have any fundamental like problems in your model, they will come up here. And if you see any errors, then you know exactly what to rectify. And then you wouldn't want to go into mapping the whole thing and then understanding, oh, that this was a major problem. So the summary basically is useful for that. But the other file that comes from this from running this software is the CSV file. So the CSV file, so both of these files are basically the outputs from running the MGWR model, and the CSV file has the parameter estimate for each point. So if I open this file, so we see it has all the rows and it has the X coordinates, Y coordinates. It basically takes the data from what we gave it, and it gives us this, all the columns starting with beta are the estimates for each of those columns. And we have one beta for each census tract in our case, and that will be true for any of the data set and whatever spatial unit you use. So this will be like minus point. So, and you can also see the range at which it varies, right? For one census tract, suppose this one, right? The average age coefficient is minus 0.002. But for this, it's like 0.19. So it's like much higher than this. Some of them are negative, some of them are positive. So this is the variation that you get to see in your parameter estimates. Whereas in the global model, you will only see one parameter estimate, which is an average of all of these. So this gives you a lot more information to map and to understand. So in terms of output, you get these data columns, which is the one that you would want to map. Now in MGWR, not all parameter estimates are significant. Some of them are not significant, and how you would judge that is by, and those are basically defined by statistical criterion of statistical significance. And how you would filter that out is by these columns called the T columns. So all the columns that begin with a T, that is for the critical value. That is like basically supposed to assign whether those parameter estimates are significant or not. So many times you would see in NGWR maps, all the parameter estimates are not mappable because we would often filter them out according to their significance. So these are the two steps that we need to do after this output comes. We need to filter out the betas according to their T values. So we have a beta column for all covariates, and we have a T value column for all covariates. And then we would want to filter these out according to whether the T value is significant or not. And then we would map only the significant parameter estimates because only those ones are interpretable. That is a very important thing that we need to understand, because there are often many studies and maps that we see where people map all the parameter estimates, and sometimes it's just noise and it's not actually significant estimates. Now these are, so then basically now at this point you can take this CSV and you can join it back to, because you have your X and Y coordinates, you can join it back to your shapefile and map it either in ArcMap or QGIS or whatever GIS software that you're used to. I often do it in Python. You can do it in Python or R or whatever, but this is your summary file that needs to be attached to a shapefile. We do not map it, and MGWR doesn't output a shapefile with it yet. That's not how it works right now. So because we have about 20 minutes, I can show you the maps that come out of it. Okay, I guess there is some chat here. Was it? Sorry. Oh. Okay, those are two good questions. So it's about first question is on multicollinearity and how they are correlated. So in MGWR, so there are two kinds of collinearity that occurs in regression and spatial regression. So in just simple regression, we would check for VIF factors, right? Because any VIF, so there is a test called the variance inflation factor test, and then you would do that VIF test for all these variables. Any variables with a VIF score of more than 10, you would discard ideally, and you would only use the rest. So then there is a call that you have to make that there are three variables which have, high multicollinearity issues, and you need to get rid of two. Then you would look at your context and your model, and you would decide which one to get rid of and which one to not. But in terms of in spatial regression, you also have multicollinearity, which is spatial, because when you do a local regression, it is possible that an entire variable is not correlated in the entire study region, but it is heavily correlated in just one area. For example, yeah, in the King County region, there is a very big lake in Seattle, and downtown Seattle is also like right there by the lake, by the water body, right? So my variable on I had also added a variable called distance to Seattle downtown because that would affect the house price a lot. But that had severe local multicollinearity issues in the Seattle region, just in the Seattle region, because the waterfront distance and the downtown distance were just exactly the same in that region. So how you would do that is by in NGWR, there is an advanced thing called the local collinearity diagnostics. If you turn it on and if you run the entire model again, you would get a local VIF value also for your entire data set. And then you would filter out, it's the same thing. It's called like a score, and it's not judged as 10, but it's just by a threshold of 30. So any value above 30 means that it has a high multicollinearity issue. So that is how you would get rid of that. And this is the test for that, which you can add on. It often takes a little longer, so I didn't run it here, but it was a good question. There was another one. Any concerns with normality in MGWR? Can you run MGWR? Yes. Yes, so you can run it. So yes, that is a very good question again. So GWR has the option of running it either with binomial or Poisson, as you see it. So you can run a Gaussian model, which is a normal model, or you can run a binomial or a Poisson. Now, basically, my summer project is to convert that into MGWR, which does not exist so far, but it is going to from fall. It's actually a similar procedure that we are trying to adapt, which was in GWR, but we haven't been able to implement it at the software level yet. But hopefully that should be available by October. And missing data. So what MGWR would do is that it would, if you have just missing rows or missing values, it would basically define it as none, and it would ignore it. That becomes a problem because in an entire column, if you have a lot of missing data, it would still calibrate the model, but your bandwidths are then just going to be global, right? Because if they are extremely global, because like it's not getting enough data, it is looking around for like, data for 40, and they're all like nans, and it's basically not being able to calibrate the model. So it will just jump to a local global scale, and it will try to take as much data as possible to calibrate the model. So if you see something like your entire bandwidth, all your bandwidth for all covariates are global, and you were like, why am I even using MGWR? I could have just used a global regression model. That is a good cue to look for, missing data in your region. But that would be something that you would have to do manually. And we have seen a few problems occur with zeros. So if you have a lot of zeros for a single covariate, a similar thing happens. Like if I have one of these variables, if they had a lot of zeros, so imagine MGWR is trying to calibrate a model for this variable, and it tries to look, and everywhere it only finds 0, 0, 0. So even though it's a binomial, it's like 0 or 1, but it's only finding zeros. It kind of assumes that the data is same everywhere, and it cannot weight it. So we have seen errors come up in data sets where those kind of data exist, and then you have to manually go and check it again. But those are just things that you have to kind of manually deal with while seeing the quality of your data and trying to understand whether and then like making a call of whether that column is important or not, and then you can possibly get rid of it. Because even I had a problem with distance to waterfront in in the case if I was doing 0 or 1, there were only a few houses around the lakes that were 1s, and all the others in the inland were all 0s, and every time it would try to calibrate, it would run into an error. So that's a problem sometimes with missing data. Many columns with the same, many rows with the same value. So that's something to watch out for. These are great questions. I think there was one more. Great. Cool. So I'm just gonna. Okay, we have about 14 minutes. But there is also right. So these are all the things that we covered. We covered all the interpretations. So if you map your results, these are the kind of maps that you would get. Like I said, there are a lot of parameter estimates that are often not they're often not significant, so you won't want to map them. You would only map the ones that are significant. I've written a short here, and if you guys, I know there's not enough time to run it right now, but it's just as a resource if you are interested in looking at, like, mapping, because I know when I started mapping in Python, it was not the most straightforward thing to do. And often we get this question about, like, okay, now we have all these parameter estimates, how do I go about mapping it? So I just, like, basically did it for this one example. And there's, I know it looks like a lot of code. Trust me, it's not. It's just like you just have to run these cells one after the other, and they all, like, play along. You'll find a folder here, which is basically which has the census tracts and that are used to join. So shape files for census tracts of King County if you want to, like, download and run this. So I already ran it, and it should run on your local computer because this is all hosted in a cloud. So when all these, like, things where I am, it's really cool actually. This was my first time with Google Collaboratory, and I realized, like, it's very interesting. So I'm installing a few things that Google Collaboratory server doesn't have. So if you run this file, this everything that I've written here should work on your system also, because basically we are all accessing the cloud and not our local computers. So it doesn't matter whether you have installed or not. It doesn't matter what packages you have installed or not. This should cover um, you. Can the Python version use multiple nodes? Can you run it on a cluster? Yes. Yes, you can run it on a cluster. I mean, like, I mean, I've used it on the HCP cluster, the Agave ASU cluster, and so how basically MGWR has its own way of parallelizing. So in the package itself, it is the backfitting algorithm is paralleled on different nodes. So if you have 30 nodes available, it will take as many nodes as your computer can offer. So now we do have that option, and how you would do that is by using mp.pool, and how then that package reads. So the Python version of the package would read your nodes in your computer that are available, and then it would use all of them. That is how it makes it faster. So I ran this software on 20,000 points. If I used only, like, the nodes that were available on my local system, it would have taken about 20 days to run. But since I used 23 nodes on the Agave cluster, it ran in 5 days. So it's very, very valuable to use those nodes. And I didn't know it wasn't available in 2018, but now it is. So that is, thank you for that question. Cool. So if you run these, I'm not going to run all of this, but basically, if you see here is where I'm filtering out the parameter estimates that are not significant, which also you want to do. So if you, like, go into this code, you will understand. Or in, like, ArcMap, it's very easy. You can just, define, show the data only where the t value for each column is more than 2.7 or less than 2.7. And these I'm using the critical t values that came out of the summary table here. I will show you, just so you guys know. So here the adjusted t value is here. These are the t values for each column, that for each covariate that you should be filtering out your betas against. So if it says 2.9, so any value where the t value is more than 2.9 or less than minus 2.9 are the betas that you should be mapping. Those are the only ones that you should be mapping. And this code basically does that here. So I'm basically filtering out according to the t critical value for each column, and defining it as these dt data t columns, all these. So these become my final filtered out values that I will be mapping then. So I just, like, adjust the code, all these projections that become really annoying if you have to do it on code, and then join the results that we just had on our CSV. And the centroid, I just did a spatial join. You can do an ID join if you have an ID, or in any way. And then basically I added the labels because it's interesting to know the context, and then we can start to interpret the results. And then I just wrote a simple function to map these different columns. So now I can map this. So basically, this is the map for square footage of living area. So you see the reds, and, like, you have this bar at the bottom. So you see 1.2 in this area versus, like, here space is not of that much value as much as it is here, and it makes sense because you see the area. Here is where Bill Gates' house is. So yeah, obviously, like, it's like a premium location, neighborhoods must be really expensive here, and more space is valued. So it basically says that an increase in square footage of living area would get you a lot more money here than it would in these suburban regions, even in comparison to these other regions. So it's pretty interesting. And then you begin to see why you would want to do this than use just a simple global regression, because that would not tell you these kind of insights that, this would. Now, this one is a water distance. Now here, actually, it's my fault that I haven't basically blocked off the water region. But here there is Lake Washington, and you see the water is like distance to waterfront is actually of significance here and is highly significant. So why is it negative? Because it says that with every mile or kilometer increase in distance from waterfront of a housing unit, your housing price goes down, which makes sense because if you're on the water, your waterfront distance is zero. And the farther you go from the waterfront, the more your house price is, the lower the house price is going to cost. So immediately you start to, and if this was, in the global regression model, you would have seen one single value and you would have been like, there is no way you can interpret this, and there's no way you can find out which waterfronts are more valuable versus not. What is that threshold distance beyond which waterfront stops mattering? And this still is like a very, it's a very cursory result that we are seeing here, because again, it's at the census tract level and these are averages that we are speaking about. But this starts really panning out a lot more if you have individual level data, or if this was not hedonic house price modeling, but like something like election data at a county level, and then you can make so much more sense of what kind of population lives where and why they would vote one versus not. Whereas in a global regression, you would not be able to understand, these intricacies of the results. So yeah, all these resources are here, and I would love for you to, explore these on your own. And okay, is there a question? Sorry. What happened? What are some other different ways you have seen? Actually, MGWR, so far it's really new. So the first paper when it was invented was 2019, and you're still seeing a surge of all these like common things being used. So there was, I think Zichi did a paper on air pollution in China and what that would be related to. I did a paper on house price modeling in Seattle, but at an individual level. So we were able to find a lot more. I think what is very interesting in NGWR that we are finding recently and is exciting is the intercept variable. So now what we are thinking is that the intercept, which is all the covariates aside, and suppose if your model is explaining 97% of the variation, then that intercept basically captures everything else that your measurable covariates can't. And we are trying to understand and project that as the measure of context. And that is very exciting. And we have seen a few other studies that have used different creative ways to measure context, because context is basically this unmeasurable perception, or like things that you basically cannot measure. And we are hoping that NGWR can be used in a creative way to answer like fundamental questions like that in spatial science. So that would be interesting. That is an interesting thing. But other fields, I would say, it's used a lot in election studies, or there was a project on teen pregnancy rates across United States. Then in Stewart's class, there were many people who used it for like, one of them used it for like is biking favorable? Sorry, like how many people bike in a particular county, and what would that be related to? So there are many different questions that you can ask with just day-to-day data. But the only problem is that you would only use it in a place where you would use regression. And that is where I see many people don't understand, NGWR versus other tools. So this is basically a regression technique, but if you're using global regression, you would much rather use this. But if you're not using regression at all, then basically there is not much use of this. So yeah, thanks for that question. Any other questions? And I'm happy to also answer any emails after this if people have any problems with their data sets, if they want to try, or if they cannot come up with a research question, if they have a question whether is this even a good regression model or not, is this even answer to software like this or not, I would be happy to answer those questions. Also, these are the resources that are available, and I would, if you guys end up trying these resources and they don't work or something, I would love to hear from you, because I'm also doing this workshop at the UCGIS symposium in June, and these are the materials that are made for it. And or actually any feedback, if you have any feedback for me of, like, the presentation style or anything, I would love to hear, because I was doing this as a dry run to prep me for that, and I would love to hear if some things worked and some things didn't work, or if I could use more time on some issue versus not. There it's going to be for 2 hours, so I'll have a little more time, but I would love to hear any feedback possible. And that's almost 1 hour. Thank you everyone for